Hey Chem 240, it's Dr. Kato. This is our second video in chapter 19, which is on thermodynamics. And in this video, we're going to concentrate on entropy. So first thing we're going to talk about is what does it mean for a reaction to be spontaneous? So spontaneous processes and entropy. A spontaneous process is a physical or chemical change that occurs by itself. It requires no continuing outside agency to make it happen. So you just put the two reactants or three reactants together at a certain temperature and pressure, and they react on their own. They don't require a spark or anything to get the energy started or get it going. So a great example is the difference between an internal combustion engine, which requires a spark, just taking air and gasoline vapor, putting it in the spark plug at a certain temperature and pressure. Even the high pressure that occurs once the piston is compressed, that's not enough to get it started. In order for the chemical reaction to occur, you need to provide an initial spark of energy that the spark plug provides. Causes an initial amount of heat from the first few molecules that react, and they cascade on in the chain reaction to make the rest of the molecules react. A diesel engine doesn't require a spark plug. Diesel engines don't have spark plugs. What happens is you put the diesel fuel together with the air under a certain temperature and pressure. It's called a compression ratio. You squeeze them together in the compression stroke, and just that squeezing puts a condition where now the pressure and temperature are enough that the chemical reaction, the combustion reaction between the diesel fuel and the oxygen occurs spontaneously. So that's what we're going to talk about. It's called the free energy of a chemical reaction. It's given the thermodynamic symbol G. But before we can understand G, the free energy, we have to learn about entropy, which is one of the two natural driving forces in the universe. Okay, so let's talk about the first one, which is that things tend to want to go downhill. So the enthalpy is an example of something that if you have a chemical reaction and its enthalpy is negative, it means it's exothermic. Well, that's a natural tendency, this tendency for things that are at very high energy or unstable to react and go downhill. So we see that with physical systems like balls that are held up in the air, or a waterfall where at the top of the waterfall, right before it goes off, the water has a lot of potential energy and it loses it as it drops off. So that you're used to from Chem 1. That delta H or delta U, which basically measure the energy of the system, there's a natural tendency for things to want to go downhill towards lower energy. But there's also an almost equally or equally important a trend in the universe that not only does things want to go downhill, they want to go to a more disordered state. Anytime the products of the chemical reaction are more messy, more spread out, have more different ways that they can be arranged, then those kinds of chemical reactions are favored. So measuring the amount of disorder that a system has is really important, and you can actually quantify the amount of disorder, and it's called the entropy of the system. It's a state function, so we give it a capital S, just like this new one, the spontaneity or the free energy, we're going to call capital G. We have capital U for the well, let me go back to capital H first. We have capital H, which is the enthalpy of the system, and U is the not the free energy, but it's the total internal energy. So if I just put them all down on one piece of paper real quickly. These are going to be our thermodynamic quantities that are state functions. U and H are measures of the temperature, right? They're related to each other. H is the measure of the heat content that something has at constant pressure. U is the total internal energy of the system. Now we have S, which is a measure of how organized or disorganized the system is. The more disorganization, the higher the entropy is going to be. So as S goes up, it goes to more disorganization. And then we're going to put them all together with G, which G is going to put together these two. Okay, and these we know, we already learned how they're related. So those are all capitals, they are all state functions, they're independent of the path. These, for a particular chemical system, like 1 mole of oxygen gas, you can find out what these values are. But more importantly, we want to see the differences in them. Delta U, delta H, delta H, delta S, and delta G. Because in a chemical reaction, we want to see the difference from, take the total, any one of these quantities at the end of the process and subtract off the initial amount, and you'll get the change in it. So the changes are more important than the absolute numbers themselves. This is what's going to count. And we're going to be specially focused on delta H, delta S, and a new one, delta G. Enthalpy, entropy, free energy. Okay, so S. S is the thermodynamic quantity that is a measure of the randomness or disorder of a system. Entropy is a state function. So with any state function, the final S value minus the initial S value tells you how much delta S is. So for any process, including something like the change of state, melting of ice, when you start with solid ice and you go to liquid water, you can look up the absolute entropy on a table, I'll show you where they are, of water in the liquid state, and subtract off the entropy of water in the solid state. Makes sense to me, and should make sense to you, that water in the liquid state has more different ways that it can be arranged, because it's not in such a tight crystal structure where each water molecule is exactly in a certain place within the crystals. Okay, the water molecules are free to move around, and they can be in many, many different orientations. So the final, the water is going to have a higher entropy value than the initial. And this has to be done at a certain temperature. So delta S at this particular temperature turns out to be 22 joules per Kelvin. And this was done usually it's done at 25 degrees Celsius or 298 Kelvin. And I'll show you where those numbers come from. From your textbook, this is Appendix C, thermodynamic quantities of substances at 298.15 Kelvin, so 25 degrees C. So what do we got to look up? We're just going to look up the H2O, and they're probably listed under oxygen. So I'm going to go to O and see if they're listed there. So this is phosphorus, here's oxygen, and maybe we'll just blow this up a little bit. All right. They're all going to be listed together. These are delta H's of formation, delta G's of formation. S's are not going to be listed as formation. They're going to be listed just in joules per mole Kelvin. Okay, so they're the only one of the three that's got Kelvin in the denominator. Okay, and here's water in the gas phase. It's got the most different ways it can be. It's the most disorganized. The molecules are all over the place, so it's going to have the highest value. 188 is huge. Water in the liquid state, 69.9. Water in the, water in the solid state. Oh, I don't know why they wouldn't have water in the solid state listed on this table. Okay, but I have it here. I must have it from a different textbook. So I have water in the solid state is going to be 41. So you take the product minus the reactant. You would usually, like you do with any time you want to find out delta S from the tables, if the coefficients were different numbers here, if they were 2, you'd have to multiply this by 2 and this by 2, but they're both 1s, so you just get them from the table and subtract them. Not surprised that delta S is a positive when I move from something that's more orderly in the solid state, the crystalline state, to the very disorganized liquid state. If I went one step further to the gas state, I'd expect delta S for that process to also be positive. Going to more disorder is the way nature works, right? And we'll talk about the reason why in a second. Okay, so gas going from the liquid to the gas would also have a positive number. Okay, so two notes here at the bottom. Delta S positive means the system moves to more disorder. Makes sense. Delta S negative means the system moves to more ordered state. That's against nature. That you have to push against it. That doesn't happen naturally. You can get it to go, but usually you have to use huge amounts of energy to do that. Classic example is the human body, right? We are so against entropy that we just have to keep on eating all day long to keep this very incredibly organized state. All of our DNA is incredibly organized. Each cell is organized. Then we're organized into tissues. Then tissues are organized into what's the next thing up? Tissues are organized into organs, and then organs are organized into systems, and then we have the whole human body. Well, in order to maintain that state of incredible order, we have to put tons and tons of energy in all day long to drive against nature. Okay, so where does this come from? Well, scientists believe it comes actually out of cosmology, that since the universe is expanding, we have this tendency for in any spontaneous process, the overall entropy in the process is actually positive. So that at the end of the process, if you take the change in entropy for the system plus the change in entropy for the surroundings, put them together, the net change, instead of it being zero, is always going to be positive. You don't have conservation of entropy in physical systems. You have, in any spontaneous reaction, every time something happens, it creates a positive entropy in the overall process of the universe. Okay, so we'll read this note here. A process occurs naturally as a result of an overall increase in the disorder. And disorder is entropy. Okay, so overall, we mean the system plus the surroundings. So delta S for the overall process of anything that's spontaneous is going to come out to be a positive number. It's going to increase the entropy of the universe. Every spontaneous process increases the entropy of the universe. Okay, we can put that into words. One way to put it into words is in the second law of thermodynamics. So the second law of thermodynamics says that the total entropy of a system and its surrounding is always increasing for a spontaneous process. Here's an example. Another way of looking at it is no process can be 100% efficient. Some energy is always lost. Okay? So the efficiency of any physical or chemical process can never be 100%. You always lose a little bit of energy to heat. So an electrical energy uses a motor, or if you have electrical energy, you can use a motor to convert it to mechanical energy. So we can create better and better, more efficient, more expensive electric motors. And someday, 500 years from now, we can have vacuum cleaners that instead of being 90% efficient like they are now, which is pretty good, we can have them be 99% efficient someday, but we're never going to get to 100%. We might even get to 99.9%, but there has to be, in order for something to happen spontaneously, you hit the switch and the vacuum cleaner goes on every time. In order for that to happen, you cannot convert all of the electrical energy into mechanical energy. Every time you do some sort of conversion, some energy has to be lost to heat, right? And that's what's happening. That's why your vacuum cleaner gets hot. Okay, you don't want it to get hot. That's why your drill gets hot. You're trying to make mechanical energy from electrical energy, but there's always waste heat that you can do nothing about. So here's another way of looking at it. Delta S then, for any spontaneous process, is going to be equal to the entropy created in the universe plus the heat of the particular chemical reaction divided by the Kelvin temperature. Okay, so if you don't know how much entropy is created and goes out into the universe, you can say this, that the entropy, if you don't know this value, but you know that it's going to be some little bit that's going to make this number go up, okay, then what's going to happen is you can get rid of this term that you don't know with a greater than sign, right? Because if you don't know what this is, and you want to take it out, you can no longer say this is equal to the Q over T. So what you can say is delta S is greater than Q over T. And again, in this chapter, all of these temperatures got to be converted to Kelvin. Okay, so for any spontaneous process, delta S is greater than Q over T. Okay. Entropy change for a phase change that occurs very slowly. Okay, we can plug into it. The Q for that phase change is delta H over T. If it happens at equilibrium and a substance is melting very slowly, then delta S, right, is equal to delta H of fusion over the Kelvin temperature. Ice melts at 0 degrees Celsius, that's 273, so that's the denominator. This you can look up in a table, right? The heat for that particular process, the Q at constant P is delta H of fusion, so that's why you're able to substitute this in for that. So there's another way to get delta S equal to 22 degrees for this process, right? Water solid going to water liquid, that was the number that we had from above. Okay? And if we do that at the equilibrium temperature, now remember, ice can melt at any temperature warmer than 0. But if you do it exactly at 0, you're going to get 22. If you do it higher than 0, right, you just have a piece of ice sitting out, what's going to happen is it's going to be 22 plus some little bit that you can't account for, the entropy that's created. Right? If you do it exactly at the equilibrium temperature, the temperature that it melts naturally, then the ice will turn into water, and the amount of entropy for that process, obviously it's positive because this guy is more randomly oriented molecules than this, and that's the 22 that we saw before. Okay, I'll just go back and show you. That's the 22 that we got from the tables when I looked them up. Okay, another way on a microscopic level to think about entropy is something called the Boltzmann equation. So the Boltzmann equation can tell you the absolute entropy, not delta S, right? This is a super simple equation. S, the entropy of a system, is equal to K, which is called the Boltzmann constant, times the natural log of W. Now W is really a wild idea. W is the number of ways that the molecules in the microstate can be arranged. So if you have a system of 7 molecules, you figure out all the different ways they can be next to each other and in the system. Count up all those ways that they possibly could be oriented, right? Take the natural log of it and multiply it by the Boltzmann constant and you will get S. So it's the number of ways of arranging the particles. So if you have a pure, perfect crystal where every atom is in exactly the right spot, like in a crystal of diamond, then there is only one way that they can be arranged, right? So if in that structure of the diamond, you would take ln of W, right, and which was 1, and the log of 1 is always 0, right? So the log of 1 is 0, so S would be 0 in those cases, if there's only one way. But most of the time, things have hundreds, even thousands, millions of different ways that they can be arranged, okay? So we know since S is a state function, doesn't matter the path that you can take, S is always S final minus S initial. Just like back over here, we wanted to know S, if we knew S final, this is the final one because it's after the arrow, minus S initial, we get 22, okay? That's take the product minus the reactant, use the coefficients as the, multiply by the coefficients if you have any. Okay, here's a great example. Oh, look what I could do. I can now, since I have my Boltzmann equation up here, and I also know that delta S is S final minus S initial, I can plug in K ln of W in for S final and also for SW. And what happens is I can factor out the K because both of them have a K. And then there's a rule for logs that the log of something minus the log of the second thing is the same as the log of the first thing divided by the second thing. Okay, so if I wanted to do it in 2 steps, let me just get a piece of paper real quick. Wanted to do this in 2 steps. My first step would be let's factor k out, right? So if I pull k out of here, go up here, right? Factor k out. So if I pull k out, I get this. ln(wf) minus ln(wi). F is for final, I is for initial. Okay, next step. Rule of logs. The log of something minus the log of something else is the same as the log of the first one, the one without the negative sign, divided by the log of the second one. Okay, so delta S then, if you want to find out how the entropy changes in a system, you take the number of ways that it exists in at the end, divide it by the number of ways that it originally existed, take the log of that. So if the numerator is greater than the denominator, that means that this is more disorganized. There's more ways that it can be arranged, right? So this divided by this, if this is a bigger number, you're going to get a positive number here, right? So when you take the log of it, not only a positive number, it's a number that's not a fraction, right? It's a number greater than 1 if this is greater than this. So if I take the log of a number greater than 1, I get a positive number. So I get some value here that's positive, times k gives me delta S that's positive. So if the system, when it's done, has more ways for it to be arranged, then let's say there's 1,000 ways for it to be arranged in the beginning, but there was only 1,000 ways for it to be arranged at the end, and 100 ways for it to be arranged in the beginning. 1,000 divided by 100 is 10. Take ln of 10. You get a positive number, 2 point something, and then multiply it by k. So that's what we'd expect. When the product is more organized, there's less different ways that it can be arranged. And this guy is a smaller number. Maybe this is 5, and down here, this is 500, right? So this one is 100 times bigger. I'd need the natural log of 1 over 100th, or the natural log of 0.01. Well, the natural log of 0.01 is going to give you a negative number. Multiply it by k, I'm going to get delta S is going to be negative. So whenever the system, the products can be arranged in more different ways, means they have, if there's more ways they can be arranged, there's more disorganization. More disorganization is going to, compared with the reactants, is going to give you a delta S that's positive. Okay, here's a classic example. If you have a deck of cards and you decide, okay, I'm going to have the cards in a super organized fashion. I'm going to decide the order and I'm going to put them in exactly that order. Well, if I decide the order, and let's say the order is we're going to start with aces, okay, then we're going to do kings, queens, jacks, 10, 9s, all the way down to 2s, right? Those are the cards. And we decide, okay, let's do diamonds first, hearts second, okay? Oops, sorry. Diamonds first, hearts second, clubs, and then spades. And every single one of them, we're going to do the aces. We're going to diamonds, hearts, clubs, spades. Then we're going to go to the 10s, do the same thing. Then go to the queens and do the same thing. Then the jacks. Then all the way down to the 2s. And I take those cards in that perfect order and I hold them. Does everybody agree? Once we made our decision as to how they were going to be arranged, there's only one way to do that. I know exactly where every card is. I know what the first card is, and I know what the last card is. The first card is going to be the ace of diamonds. The last card is going to be the 2 of spades. And I could predict every single one. Guys, that's only one way, right? Pretty boring. All right, throw those out. Throw them out, right? Hold them in your hand so they're high up in the air, so they have a lot of energy. And I throw them out. Well, they get rearranged and they go all over the floor. This time I just pick them up any old way. I just grab them. I don't think about it at all, right? I just pick them up. Well, if I wanted to predict what order those cards would be in, right? That would be 52 factorial ways. And what is 52 factorial? Well, You don't know which card you're going to pick up first, so there's 52 original choices. So that's 52, right? Once you pick up that first card, there's only 51 cards left, but you have no idea which one you're picking up, so you have to multiply by 51. Once the first two are established, there's only 50 left. So what happens? You have to work your way all the way down to 1. That's what 52 exclamation point means. 52 factorial. If your calculator has a factorial button, you can try it out. 52 factorial comes out to 1.55 times 10 to the 66th. That's a huge number of ways. Okay, put that into my calculation. I take the ln of, there's only one way for the bottom, the ln of 1.55 times 10 to the 66th divided by 1 is still 1.55 times 10 to the 66th. Take the natural log of that, multiply it by k. What's k? Here's the value of k, 1.38 times 10 to the negative 23. If I do all of that, I get delta S is equal to 2.1 times 10 to the minus 21st joules per Kelvin. Okay, that would be if there was one particular molecule and there were 52 different ways that it could be arranged. Okay, now, why is this number so small? Because that's for just one deck of cards. Well, one deck of cards is kind of one microsystem. We have millions and millions and millions of molecules. So if I wanted to know what this is for a mole of molecules, I would have to take it and multiply by Avogadro's number, which is 6.02 times 10 to the 23rd, and I'd get a delta S that would be something like 100, right? This is joules per K, kind of per molecule. Okay, for our simple example there. Okay, so we have the second law of thermodynamics, right? We're doing all three laws of thermodynamics this chapter. The second law of thermodynamics talks about efficiency, talks about in any spontaneous process, right? In any spontaneous process. Oh, sorry, let me just make sure I got the right page. You did that, good. Third law of thermodynamics is right here. So second law says in any spontaneous process, delta S for the overall process has got to be positive, right? So system plus surroundings, it'll always be positive because we live in an expanding universe. First law of thermodynamics, all the way back in the beginning of chapter, was very straightforward, right? What was it? It was Q plus W, right? So delta U is equal to Q plus W. That's the first law of thermodynamics. The second law was just one we just started with right now. And that is delta S in any spontaneous process has to be greater than Q over T, where T is in Kelvin. Here's the third law of thermodynamics. Third law of thermodynamics isn't an equation, it's just a statement. It says that a substance that is perfectly crystalline at 0 degrees Kelvin has an entropy of 0. There's only one way that it can be arranged. Okay, so for my diamond crystal, not only did I have to have a pure, perfect crystal of carbon, but I'd have to lower the temperature all the way down to absolute 0. Okay, and if there's only one way that it can be arranged, you plug it in the in the Boltzmann equation. The log of 1 is 0. 0 times K gives you 0. So how do you have something with an entropy of 0? It's the same. It's a statement of the third law of thermodynamics. A substance that is perfectly crystalline at 0 K will have an entropy of 0. Okay, so next note has to do with S0. So S0s are these tabulated numbers that are in textbooks that you can use to do problems. Okay, so we talked about them. They don't have their own table, which is good that they don't have their own table. They're in a table with, it is in your textbook, table C, right? And they're in there with delta H 0 of formation, delta G 0 of formation, and then just S. S is the absolute entropy of these molecules. How much disorganization do they have in that particular state? So here's ozone gas, right? Make sure you have to make sure you look up the gas state. Okay, here's oxygen 0, here's oxygen O2 gas. It has an entropy of 205. An oxygen atom has less entropy because it vibrates less. There's only one atom. It has one of 161. Okay, so you can look up those numbers. So the standard entropy, S0, is the entropy value for 1 mole of a substance at standard conditions. All gases are 1 atmosphere. All solutions are 1 molar. Okay, so 1 molar is the standard concentration. 1 atmosphere is the standard pressure. And the temperature doesn't come with a little 0. You also have to state the temperature. So table 18.1 gives these values at 25 degrees. And all the tables in all the books will always do it at 25 degrees. But it is important that you realize this little 0 does not cover the temperature. You also have to say the temperature. This covers the concentration and the pressure. Pressures are 1 atmosphere of any gases, and any solutions are at 1 molar. Good? All right. Okay. Note, the elements have non-zero values, unlike delta H0 formation values. Show you that really quickly. Look at O2 gas, right? O2 gas has a delta H0 of 0 and a delta G0 of 0. So those formation numbers, those little f's, let me make this a little bigger. Okay. Those little f's mean how much energy does it take, right? Delta H0 of formation. How much energy under standard conditions and 25 degrees does it take to make 1 mole of oxygen gas from its elements? Well, it's 0 because it's the same thing. It doesn't take any energy to make oxygen from oxygen. It takes energy to make ozone because that's not the natural way you form oxygen. So you're going to get zeros in these tables in a lot of places. Whenever, here's scandium, whenever you're making the element from the element, that doesn't take any energy. Okay? Here, this would be to go from the solid all the way to the gas phase. So that takes energy to go from here to here. Okay? Good. Same thing with the free energy. The free energies are of formation, which means how much energy, how much free energy does it take to make oxygen gas from oxygen gas? It takes 0, okay? Because the definition is to make it from its element. If it's already an element, it's not going to take any energy. That's not the case. Look at S. S is not a delta S0 of formation. That would be 0. S is just the absolute entropy at 25 degrees. How much randomness does 1 mole of oxygen gas have? It's the only number I know that's tabulated in its natural state. These guys are hard to get. Okay? Okay, so look, this next note looks familiar, okay? How do you work with them? If you want to get delta S, the change in entropy for a particular chemical reaction, you take the S0s from the table for the products, and you subtract the S0 from the table for the reactants, and you include the coefficients in there. So if I have an overall chemical reaction, let me see if I have a chemical reaction around here. Right? If I had this chemical reaction up here and I wanted to calculate delta S, I would take this guy, look it up, this guy times 2, write those two down. I got to take the products first. So this plus this guy times 2 minus all the reactants. So that's this one, methane in the gas state, times 1. And then O2 in the gas state times 2. So products minus reactants, where the coefficients get multiplied by the numbers from the tables. Let's look at that one more time. Just like delta H, and it's going to turn out to be just like delta G. Products minus reactant, the sum of the products minus the sum of the reactants. That's what this symbol is. This fancy symbol is sum. Sum of the products minus the reactants, take into account the coefficients. Okay, do all the products and put a parentheses around them so you don't get confused, then subtract off all of the reactants, okay? All right, so next section, I'm gonna stop right there, and the next video I will start with predicting the sign of the reaction. I have an alarm clock going off now, sorry about that. So predicting the delta S sign in a reaction. So these are questions I could ask multiple choice of, and no math. You're just going to look at the particular situation and make a determination. Do I think that this is moving to more randomness, or is it moving to more organization? If it's moving to more randomness, delta S is going to be positive. Moving to more organization, delta S is going to be negative. Remember, the universe is expanding. It's natural to keep your room messy, okay? Things don't go perfectly. Look, I'm giving the lecture and there's a alarm clock going off in the background. Okay? Get used to it. Life's not perfect.